design. All the things I'll be teaching the theory part basically, that is taken from this book. Okay, so I'll share this book with you, and what you will do, I'll suggest the chapters. From that chapter, you will be reading that topic which I am mentioning in the slides. Okay, so it's a huge essay, I think 600 or 800 pages book. So from there you have to find out your topic and you have to read it. Got it? So let's start with GPR equipment. So there are several pioneer manufacturer are available nowadays. More GPR systems are available. So generally GPR works in the ground condition. Okay, so ground or near to the ground condition, that all will be discussed. So the company is a GSSI, Geophysical Survey System Incorporation. Then there is Mala GPR. Mala GPR is from ABEM. ABEM is also a famous geophysical or geophysical instrument manufacturing company. IDS Georadar is there, and other GPR companies is there. Nowadays, in 2019, I think people have proposed for airborne GPR. This is for shallow investigation, very shallow. I mean, up to half meter. So you want to know about the pavement or road condition. So this drone GPR can help you to do that. So everything will be discussed. So what's the main equipment or what's the main criteria of GPR? So this figure I have explained it already. So GPR has three main component GPR instrument. One is antenna. Antenna means transmitter and receiver. I'm mentioning both. Okay. Another one is receiver, and antenna means transmitter and receiver. Then is your control unit that I have written here as display. So display and processor comes under the control unit nowadays. So control unit will be your a portable computer kind of thing. Some of the system comes with the laptop. Okay, so that will be your control unit. You will be defining some parameters, and that according to that parameter, you will be taking the data. So I'll be explaining GPR in details because these things might be very much helpful for your research in near future. Okay, so try to understand this. And the received waveform will be, so there is a dielectric constant air and this blue layer, first layer. So first layer and air has a dielectric constant that will give you this peak, and there will be a dielectric constant contrast here, and there this will give also another peak. So this is how the GPS signals look like or recorded. And by combining all the, this is called the stacking, by combining all the traces, few more terms, so it's a huge thing. Okay, so this all the theories are derived from the seismic reflection and refraction technologies. So these things should be understandable, not just like 2 or 3 classes. It required a dedicated semester for that. Okay, so I'll not go much deeper on that. So first you understand what we generally do. This type of traces we will be recording and we will be stacking it. What do you mean by stacking? You will be sending pulses. We are sending generally pulses here. Not single pulses will be recorded here. So I'll be defined here. So say 32 stack. That means that you will go 32 times and it will be summed. The summation term will be there. So after summing all the data, then it can be visible more properly. Okay. So that is called the stacking. Remember that. Now, GPR equipment, what I have holding here, I held here. So this is the control unit. This is the portable computer, and this is the cable. Okay, connecting with this system. So this black cable is connecting with this system. Okay, it's called the coaxial cable. And this instrument is the 200 megahertz GPR instrument, and this wheel is for the calibration. So just like a speedometer in bike or in other bike or in car, there is a speedometer. Same speedometer principle is applying here. So this is called the calibration wheel, or this is basically, or this is called the survey wheel. This basically measures the distance you are traveling. So you will be calibrating. So this much of rotation equals to this meter, and from there you will be getting the idea or the distance you have covered. Okay. And this is this antenna basically consists of two coils, just like any electromagnetic system we have discussed, just like the TM system. And these coils vibrating at center frequency of 200 megahertz, and it's emitting pulses. So this is a monostatic antenna. Here the transmitter receiver theoretically in the same position, but practically it has a separation of a few centimeter. Okay. So this side, let's say there is a transmitter, and this side there is a receiver, and I have we have extended a straight line here, and along this straight line we are taking the data. So the scanning result will be, you have to keep the the instrument in the middle. Okay. So the middle portion of the instrument will be kept here. There is a point there in this portion, and this middle point, actually they are measuring the middle point. One side there is a transmitter and one side is receiver, so middle point is mapping. So we are basically mapping the middle point using this system. So the main components of a ground penetrating radar is control unit, antenna, power supply. So control unit is your computer or laptop. Some of the places the laptop is there, and antenna is the transmitter receiver. So this could be monostatic or bistatic, that will be discussed in details. And there is power supply. So we generally use here as a lithium-ion battery. So there are several lithium-ion battery like this was there. So they provided me two batteries, and these two batteries were enough for do the survey a day long. So it can extend, or it can survey up to 1 day. 1 day means we used to go to the field at 8 or 7, and we used to come back at 4 or 5. Okay. So this will be the lithium-ion battery, just like a mobile battery. Have you seen a mobile battery in a old Nokia phone? Okay, so just like a mobile battery, but it has a bigger size. That battery, bigger size, and it's basically not thicker. It's a thin rectangular shaped structure. Okay, so these batteries are used as a power supply. Okay. So if I want to explain the GPR equipment, GPR equipment means data electronics, antenna, data digitizer, computer, and display module. So this data digitizer, computer, and display module data is basically included in the control unit nowadays. Okay. So GPR has several types. One is your impulse type, that we generally use the impulse type, and another one is the continuous wave type. So one thing you can do, you can use the impulse, then of time, you can use the impulse or 10 of impulse, or you can use the signal like this. It's a continuous type. Okay. So this is the continuous type CW, and this is the impulse type. We generally use the impulse type. We generally prefer the impulse type, and I will discuss how the impulse, why we generally use impulse type, what's the advantages and disadvantages of the impulse type, and what is the advantages of continuous wave type. That will be discussed. So impulse radar basically operates in the time domain, while continuous wave radar operates in the frequency domain. Theoretically, impulse and the continuous wave radar with identical specification and parameters will perform identically. These radar system and the basic design of these two types are presented along the advantages, and this will be presented here. So there are most two categories of GPR, as I was mentioning, impulse and continuous wave. So most of the GPR system you will find commercially available. Whatever the companies I have shown you, they basically manufactured the impulse wave GPR system, impulse radar technique. And continuous wave, basically continuous wave stepped frequency radars have been developed over past decade after 1994, and though most have involved the is basically for the research purposes. For commercially, we generally use the impulse radar. Okay. Now, what are the impulse radar? You have to understand the basic difference, and you have to understand why these impulse radars are important than the continuous wave radars. So it's basically acquire data just like a TAME method, TEM method, time domain electromagnetic or transient electromagnetic method I've already discussed. So just like a TAME, not just like a TAME, it's a TAME technique. Okay. We are simply using the pulses and recording the received signal. So acquired data in time domain are generally known as impulse. It's a TAME technique, basically impulse radars. And time domain pulse is transmitted and reflected. Energy is received as a function of time. So the resulting waveform basically indicates the amplitude of the energy scattered from the subsurface object versus time. So range information is based on the time of flight principle. So it's basically include using the amplitude and two-way travel time. And the simple display of the radar return is in called an A-scope presentation. What do you mean by A-scope, A-scope, B-scope? There is a A-scan, B-scan, C-scan is there. So when we are presenting single waveform, that's called the A-scope. B scan for your 2D section, and so there will be lot of signals. So this side is the distance and this side will be the time. Okay, lot of signals. Okay, and C-scope will give you the idea of the 3D. So how 3D data was made? 3D basically made using the 2D signals. So this line, along this line you will have the 2D signals like this. Then along this line you will have the 2D signals. Okay, along this line you will have the data, and along this line you will have the data like this, and like this you will have the data. These are the profile traverses. Okay, this is how 3D area or 3D survey was done. So and this antenna basically plays a major function in the impulse GPR system dynamics. So what are the advantages of the impulse reader? Because it's very simple of manufacturing and it is less cost than the CW continuous wave frequency system. So we generally use CW, continuous wave GPR only for research purposes. The disadvantages includes undesirable ringing. So ringing, what do you mean by ringing? Ringing means the noises it comes. These are the noises. So you'll be having several horizontal lines, and it is very common associated with the GPS system. So suppose you are surveying on the subsurface electrical current cable. So there is a electrical pipe or electrical cable going in the underground, and you are surveying over that. Then you will have this ringing kind of effect. Or there is a void space here, then that will give you the ringing kind of effect. Okay. Strong coupling with the ground or the void space there will be reverberating, and it will give this ringing this straight parallel lines. It calls the ringing effect. So due to this ringing you cannot see what's below this data. So generally we have to remove ringing by some some processing technique, but it is not desirable that you get ringing in during field work. Okay. So the disadvantage here is the ringing, and I'll discuss about the ringing more with some example. And the inefficient use of the transmit power, low duty cycle, and the resolution limited by the pulse width. Other difficulties involve sampling of wideband signals with slow speed sequential digitizer. Okay. There is another type is called the step frequency modulated continuous wave. Frequency modulated means FM. The same principle we are using here, the FM principle, the FM radio we used to hear. Same principle we will be using here, and the transmitting frequency is stepped. So what do you mean by stepped? So if the frequency is look like this, is the frequency like this, this will be your transmitting signal from the transmitter, and this is called your step frequency. So here step frequency generally used, and the advantages of step frequency GPR are control transmission frequencies. It has a efficient use of power, that is very important, and the nature of this system basically allows you to collection of the real and imaginary data, which allows the complex processing and implementation of SAR algorithm. So disadvantages of step frequency includes the complex electronics. The electronics part is complex, so that will be most costlier than the previous one, impulse radar, and requirement of DSP. And also time varying gain cannot be applied to the return system, and several disadvantages are there. But this continuous mode generally not used for commercial purpose or for our geological or geophysical investigation. Okay, we generally use the impulse radar. Remember that. Now, few things before describing about the antenna. Few things you should know about the few parameters. We basically classifying the antenna, and this parameter will be mentioned like the dynamic range. Dynamic range of a um, antenna can be written like the ratio of largest receivable signal to the minimal receivable signal. How large signal? What is the ratio of the large? I mean maximum and minimum signal, Vmax and Vmin. In the logarithmic scale, it will give you the unit dB. So in decibels, you will have the dynamic range. So whenever you will be purchasing the equipment, there you have to see the dynamic range. Just like you are buying a phone and you are saying, okay, this phone is giving 48 megapixel at this price, and this phone is giving 36 megapixel this price. Just like that, you have to go for the dynamic range. You have to look after the dynamic range. That okay, this is giving this decibel of dynamic range, and this is giving this decibel of dynamic range. This is the things you should look after when you will be purchasing. Okay, so whole lot of things has given here. I'll suggest you to read it. Next is bandwidth. This is very important. Let me talk you about a signal, any signal. Let's take a sinusoidal signal. I'm talking about sinusoidal signal. Sinusoidal signal means it's a sine wave. How sine wave generally occur? Look like this is a sine wave. Okay. Now, in this sine wave, there will be. So this is sine wave. So this side is the amplitude, and this side is the time. Now let's take this portion. I'll be zooming this portion here. This is the whole signal. Okay, but in our instrument there is some capacity, or there is some limit. Okay, you cannot record all the signals. So a whole lot of GPR frequencies are present in environments, like you are using mobile, you are using radio. So you cannot be you cannot record the whole signal. Okay, so all the frequencies you cannot record, then it will be a hazy thing. Okay, I mean, so most of the electronics basically uses the electromagnetic waves, and these electromagnetic waves are signals are present uh, in that area. So these EM signals you cannot collect all the frequencies. That will overwhelm the system. That will actually do many problems. Okay, so what we generally do choose a range, and within that range we'll be taking the recording. Okay, so we'll be, suppose the frequency is coming around 10 megahertz, let's for your sake to 11 megahertz for a simple example. That's the area we are most interested. That's the frequency we are most interested. So what we'll do, we'll be using filter, high pass filter, low pass filter, band pass filter is there. So what filtering basically does, filtering generally cut the frequencies. This frequency, low frequency will be not recorded, and high frequency greater than 11 megahertz will not be recorded. Now let's talk about the filter, then I'll go for the bandwidth. So whole lot of frequencies are there, but we will be considering, if I plot frequency here, but we will be considering of certain range. Now let's talk about the low pass filter. Low pass filter means, as the name suggesting, it will be passing the low frequencies. Okay, so this low pass filter will be passing this frequency is increasing this side. So low pass filter will passing the frequency, low frequency below that. So only these frequencies will be there. Okay, for the low pass filter. For the high pass filter, it will allow on the high frequencies below of which. So I have defined that up to 10 megahertz. After 10 megahertz, will be recording. After 10 megahertz, so our high pass filter will be at 10 megahertz. Okay, and this data will be recorded. Below 10 megahertz, no frequencies will be recorded. Okay. Now this is called the high pass filter. High pass. Now what is a band pass filter? Band pass filter is between the low pass filter and high pass filter. So sometimes, so there is a huge probability, or there is a huge chance that all the frequencies can recorded, which is not desirable. So we want 10 megahertz to 11 megahertz up to this. So why we are not specifying that? So for that reason, suppose we want to specify it, this is 9 megahertz and this is 10 megahertz. So after specifying this is called the band pass filter. So band pass filter will give you the idea of, it will allow a range. Okay, and that's most acceptable always. In all the cases, in seismic equipment, in GPR equipment, we generally use the band pass filter. So band pass filter will give you the idea. Suppose we are using 200 megahertz antenna. Here I generally used to take 100 megahertz as a low pass to 300 megahertz as a high pass. So in between 100 to 300 megahertz, we generally used to take this data. Okay, so for the 200 megahertz GPR signal or receiver or GPR investigation, we generally keep filter at 100 megahertz and 300 megahertz. Why? We are taking within that range. Below or beyond 300 megahertz, that won't be recorded. Below 100 megahertz, that won't be recorded. That's why you can actually get the signal. Okay, so there are some thumb rule and other things is there. Now let me talk about how what is a bandwidth. Bandwidth means the frequency, maximum frequency minus the minimum frequency. That's the simple definition of a bandwidth. That's the maximum frequency now and the minimum frequency. And this is for the continuous wave. So if I draw a continuous wave this step frequency or frequency modulated FMCW. So this is the minimum frequency, this is the maximum frequency, that will be the bandwidth. Similarly, here this will be the bandwidth, and both are the same. I couldn't draw it properly. It is symmetric style. It is basically symmetric up to this. Okay, so this is called the bandwidth. But for the impulse radar, we have only one signal of short duration, and let's say the signal duration is tau p. So B bandwidth will be 1 by tau p. Okay, and this should already this should be noticed when you will be purchasing. These are the features. Just like you are buying an instrument, these are the features of GPR instrument. Before without checking it, don't buy it. Okay. Center frequency, that's very important. Center frequency is that, see, I told you that the my antenna is 200 megahertz, but it won't give you the 200 megahertz since the pulse it will create. I'm telling you the impulse, but the impulse will have kind of the structure like this. It will not be sharp as we generally represent. So this is the 200 megahertz that called the center frequency. At the middle, it is 200 megahertz, and the minimum will be, so there will be a F minimum and there will be a F maximum, maybe 200 megahertz plus minus 1 megahertz. Plus minus 1 megahertz. So this side, that means this side will be 1 megahertz, 201 megahertz, and this will be 199 megahertz. Okay, so it's basically where we are saying that it's an impulse radar. You don't have any bandwidth. Its bandwidth nearly to the its bandwidth is inverse of the duration, because you cannot find out the max and minimum. But in practical, it's very difficult to generate impulses, and it's somehow not this type of this shape. It will come like this, and it will give you a sense of a minimum and a maximum. So when there is a minimum and a maximum, so you can that will also be specified, and middle of the frequency is, and that middle frequency or center frequency is called the 200 megahertz frequency. Okay. So there are several expressions. Is that bandwidth does not define GPR frequency. A frequency band anywhere in the spectrum will satisfy resolution needs. So ground penetrating radar signal characterized by the bandwidth to center frequency ratio R equals to B by FC. We in every effort we basically want to make R as large as possible. Okay. So read it from the book I'll provide to you. Now range resolution. The range resolution is the ability of radar to resolve between two closely spaced targets is called the range resolution. What do you mean by resolution? I have already want to describe resolution that, let's say two points are there, A and B, two closely spacing point. If your signal or two targets, that you can understand better. So suppose there is two target, one A and another B, A and B. Now you are using GPR to scan the area. If your GPR system is capable or enough to differentiate between two closely spacing target like AB, then your GPR signal has high resolution. If not, if it's appearing as a single target, then it will be of low resolution. Okay, so generally high frequency signals, high frequency GPR has the high resolution and low depth of penetration. Okay, now let's give you another real example, that laminar beds. You know laminar beds, laminations in sand, and these laminar beds, if you are using the high resolution system like a 400 megahertz system you are using, you can delineate this laminar bed easily, because it might be, it's a very thin bed. You know the lamination? What do you mean by lamination, geologist? What do you mean
Sir,
by
So
lamination?
less than 1
sir,
centimeter beds are known as
yes, sir.
laminar.
So what, less than 1 centimeter is a very thin bed. If you are using 400 megahertz antenna and above of which you have
So
some
less
sandy
than 1
layers,
centimeter
okay,
beds are referred to as laminar.
lamina. Okay, so there is a lamina is there. This
Yes, sir.
lamina, and this lamina can only be understand when the resolution is high enough. Okay, if you are using less frequency like 10 megahertz frequency you are using, that is very less than 400 megahertz. 400 megahertz system is high resolution system. So 10 megahertz system is a lesser, very lesser than the 400 megahertz. Then you might not see this in the data. Okay, so that's how the range resolution work. And range resolution, the theory of operations, um, the ability of the radar to resolve between two closely spaced targets. Remember that you might have to write this short notes on this thing also. So in your exam, so the ability of radar to resolve between two closely spaced target is called the range resolution. And two targets separates in time can be distinguished if the envelopes of their respective transient returns are clearly separated. Okay, half width, half power, you want to understand. So range resolution can be explained by 1.39 C divided by twice B root over of epsilon R. So epsilon R is your dielectric constant or the relative dielectric permittivity, and this is how resolution changes with the bandwidth. So if you are using the 1000 megahertz, this is see the range resolution. So 20 up to 20 centimeter thickness. So there is a laminar bed, or there is a small bed, there is let's say, and if the bed is in dry condition where the dielectric constant is higher, then less than 10 centimeter thickness bed can be, or less than it will be, how much it will be, less than 5 centimeter. So 5 centimeter thickness bed can be resolved, can be seen using this system. Which system? 1000 megahertz. But when you are using 62.5 megahertz, that's very low. The resolution only so this up to, let's see, it's a 70, only 70 centimeter thickness. Okay. So if there is a 5 centimeter thickness and you are using 62.5 megahertz frequency, then you cannot see that layer, that laminar layer, or that 5 centimeter or that thin layer. That will appear as a single layer. Okay. That's the basic fundamental principle of the resolution. This is called the range resolution. A lateral resolution basically depends on the velocity, pulse width, and the distance from the system. The larger the distance, the greater the lateral resolution length happen. And lateral resolution basically closely related to the Fresnel zone. And Fresnel zone basically give you the idea of there is a transmitter and there is a receiver. It creates a zone like this, elliptical zone. This is first Fresnel zone, second Fresnel zone, third Fresnel zone, like this. Okay, there is elliptic, not like this. This one first, then second Fresnel zone, and generally lateral resolution is equal to the first Fresnel zone. Okay, and this Fresnel zone idea basically developed after the diffraction effect done by this Fresnel scientist, and they actually use a slit kind of structure, and this slit, through this slit they passes the light, and that will appear, that will give you an idea of lighted portion, then darker portion. Some portion will be the darker, so this will be the darker portion. Okay, then again the lighter portion is there, then the darker portion will be there. It will be the concentric band of alternate darker and lighter bands. Okay, concentric, alternate, darker and lighter. But I couldn't draw it. It will be circles. Okay, so this circle will give you the first Fresnel zone, this one, and this will be your second Fresnel zone. this first fractional zone is actually related to the lateral resolution. So one more thing is there is the unambiguous range. So for the farthest distance that the target can determine without analyzing occurring is called the unambiguous range or the Rmax. So Rmax can be written as it depends on the pulse repetition frequency, how many times you are giving the pulses, and pulse repetition interval. So what is pulse repetition frequency, pulse repetition interval? This is TP, tau p. This is transmitted pulse. You will give just like a TAME method. It's a the basic principle of pulse or impulse radar or impulse GPR based on the TAME technique. So here we have a off time, we have a on time, and this on time you are giving a pulse. This pulse is a duration of tau p. First one, there is a off time, that is TR. So TR means your pulse repetition interval. That interval, this interval between these two is called the PRI, pulse repetition interval. And pulse repetition frequency PRF, the frequency you are giving there. So frequency is 1 by PRI. So TR is commonly referred to the programmable time window of pulse repetition interval. See this. Or PRF, how would you find the PRF? You see physically, you have seen the PRI, that's pulse repetition interval. PRF can be estimated by inversing the PRI. PRF equals to 1 by PRI. Okay. So now there is a formula to calculate it. Rmax equals to CTR divided by root over 2 root K or epsilon R. So that's the formula of Rmax. And for step frequency continuous wave radar, that's for the impulse radar, it will give you NC equals to 4B root epsilon R. So there's a number of frequency steps. So now a control antenna or the impulse radar technique work is a transmitting, they are basically transmitting a signal, and it will be reflected from the target or the boundaries, and it will be recorded. Then sampler is there, low speed analog to digital converter is there, delay time is introduced, control and record basically is a, this is done by the control unit. So this is a simple diagram, and this is a generally the pulse you will be using, or we have been using for impulse radar technique. Now let's talk about antenna. Antenna generally transmit energy and it can receive energy. So which transmit energy is called transmitter, which receive energy is called the receiver. An antenna can be classified into two general classes, omnidirectional and directional. So what do you mean by omnidirectional? Omnidirectional means its radius in all the directions. So there is a coil like this, solenoid, ever solenoid, I think you have the idea now. Just like a EM, so this type of coil will be there. This is the transmitter coil, and there will be the receiver electronics in there, in between a system, and that's in a monostatic system. Another in the bistatic system, transmitter and receiver are separate. Okay. So in this transmitter, in this receiver system, so transmitter basically transmitting a frequency. Okay, and this antenna transmitter can from our concept of electrical thing, you have also seen that it can go up to 360-degree angle, or if it's a ground coupled antenna, then it will go a semicircle. So it can go this side, it will be going this side, it will be going this side, and it will be going this side. That is called the omnidirectional. But for the directional, you will be focused on single direction propagation. Okay, so we generally use the omnidirectional, and this is the relates to the concept of the isotropic antenna, which is one that radiate energy uniform in all directions. I mean in 360-degree, and is useful. Okay. and it is a useful if fictitious concept to enable real antenna characteristics to be referenced. Directional antennas radiate energy in pattern of lobes or beams. Generally, directional antenna you will find that it's radiating energy like this. Okay, so this is called there will be a main lobe here, and this is the side lobe. This is the side lobe. This is the side lobe, and this is the main lobe. So this is how directional the radiated energy patterns lobes or beam that extend outward from the antenna in a one direction is given antenna position. So radiation pattern also contains minor lobes, otherwise known as the side lobes. And it has two main characteristics: directivity and power gain. So directivity, what is directivity? Directivity means the directivity of an antenna refers to the degree of sharpness of beam. Okay. B means the signal you are transmitting, how sharp the signal is, that is your directivity. If your signal is less directivity, or if your signal is wide, then the dispersion characteristics will be more, but if it's sharp, then the dispersion characteristics will be less. Okay, so the dispersion will be less in case of sharp things. So that's why that's the thing directivity basically means. If the beam is narrow in either azimuth or elevation plane, the antenna is said to have high directivity. If it's narrow, it's a very what we theoretically presumed or what we theoretically want to develop. If your beam is indicating in that direction, that will give you the high directivity in that plane. Conversely, if the beam is wide in either plane, the antenna is said to have low directivity in that plane. Thus, if an antenna has a narrow azimuthal beam, a wide elevation means the horizontal directivity is high and vertical directivity is low. So these are the parameters we will be looking after. Directivity means maximum radiation intensity divided by average radiation. This is the directive gain. So maximum radiation intensity divided by the average radiation intensity. We'll be reading it from the book. Now there is another another characteristics of this antenna is called power gain. The power gain of antenna is basically related to the or directly related to the directivity and the ratio of the radiated power to the reference dipole. There is a term here introduced is antenna under test. So when you are manufacturing an antenna, in order to measure the power gain, so your dipole, the reference dipole should be excited or fed in the same manner, and each must have radiated from the same position. Okay. So read it from the book. It is very easy to understand. So in more conventional radar system, the fields of the antenna are classified as near field and far field. This is very important. Remember that. So near field, also called the reactive near field region, is the region closest to the transmitting antenna, for which the reactive field dominates over the radiative field. So what the field the reactive field means the fields coming from the target, and radiative fields means you are what the field you are giving. So this near field condition is giving you called the reactive near field region is the region that is closest to the transmitting antenna. And here the reactive means for obvious reason the reaction if there is a conductor body present there, the reaction will be larger than the radiative fields. In the far field condition is called the Fraunhofer zone, and the region where the radiation pattern is independent of the distance from the transmitting antenna. And in the far field, the power received per antenna from the isotopic antenna is calculated by so PT, total power received, divided by total surface area. It's a spherical consideration we are taking. So when the beam propagates or the beam radiates from the antenna, it propagates in a spherical manner. So this is works this way. So this is the azimuth, and this type of curves are given. What is a gain? Gain can be divided, gain can be explained is the widely used parameter. And gain, when you will be buying an antenna, you should go for the gain also. You should look after the gain also. So the gain of an antenna can be expressed at 10 log 10 numerical of numerical gain. So 10 log time is generally expressed as a in decimal, also is expressed as a dpi. Okay, so generally we denote gain as a dpi. So this is how a trace, or this is how a GPS signal look like transmitted. And the gain, the amplitude gain will be looking like this. So what is the range of GPR signal? The GPR antenna has a range of 10 megahertz to 2.6 gigahertz. And these things in between 10 megahertz, so this is very important. 10 megahertz to 2.6 gigahertz is available commercially. Okay, and this antenna can be broadly or commercially defined in two types: ground coupled and air coupled. So in air coupled antenna, what we do, we kept the antennas at some height from the ground surface. Okay, and this is how the target reflection, ground reflection, bottom reflection, one trace. This is called a trace. So one signal, one received signal is called trace. So one trace of GPR signal will look like this if there is a target like here. Okay, by combining all the signal you will have a 2D section, but SF is for 1D structure. Okay, for ground coupled GPR, we are basically keeping the antenna on the ground. So air coupled system basically worked for quick survey. Just you mounted it on the vehicle, and it will be fine. Okay, for the ground coupled system we generally use for, so air coupled system give you the idea of hardly up to half meter, 0.5 meter, or 0.75 meter or 1 meter. But ground coupled system can look up to 50 meter in the subsurface. Okay, so we generally, as a geologist or geophysicist, we generally go for the ground coupled system. We do not use the air coupled system. This is basically this air coupled system. This is the example of the air coupled system. It's called the horn antenna. So several names are there. So this is the GSSI horn antenna, 2 gigahertz, and it will generally used to inspect the road. So there is a GPS mounted, there is antenna receiver mounted, and it can collect the data at high velocity. Like you are driving the car at 10 kilometer per hour or 20 kilometer per hour, it can collect the data. Okay, so if I want to know what our contractor has done with the road, they have used enough asphalt or enough road materials, that can be surveyed by this. How Indians do, we generally dig there. We generally dig a portion and then we see, okay, they have mixed oil. But the contractor or that guys are very clever. They know where they will dig. Okay, so that's why the road condition in India is so bad here. In generally, in outside country, they mapped whole the road with this antenna or with this GPR technique, and they find out that okay, this much thickness was asphalt and this was the condition, and this much they have provided. They have not provided according to the marks. That's why I won't pay you that much. Okay, or I will hold his payment until unless they are making it better. So there, this is a technique to see how good the work has been done. Okay, so the antenna basically designed the application requiring very high resolution comparing within 0.5 meter. Okay, so not it won't see up to 50 meter or 10 meter. It will go up to hardly 1 meter. Okay, and for road work or for any quick survey work, 1 meter is enough. So suppose there is cemented pavement is there, or there is some bridge work is there, and you want to inspect the bridge material, then you can use this material. It's a very faster technique, very fast. Like you are driving the car and data will be recorded automatically. First, once you program the system, it can record automatically. Got it? Now there is a ground coupled antenna. So these are the ground couple antenna we have fortunate to watch. So this is the control unit and this is connected with this ground couple antenna. This is 200 megahertz monostatic antenna. What do you mean by monostatic antenna? Sagota. Sagota, hello.
Yes,
Hello.
sir.
What do you mean by monostatic antenna? Monostatic antenna are those where the transmitter receiver don't has theoretically transmitter receivers are co-located, means they are in the same position. This type of antennas are the monostatic antenna, and this type of antenna is the biostatic antenna, because this guy what he has holding I mean what he's holding here in this picture is the transmitter, and this he has holding the receiver. So there is a certain gap between transmitter and receiver, you have to keep it the certain gap, and the middle point there is a nail. If you could see here this nail, so we are basically doing the just like the resistivity sounding, we are doing that sounding, and same sounding principle or same thing we'll be doing. So we'll be moving away from each other. So after taking the data, all signal it from here. So, okay, I've taken this trace. You go for the next one. Give me a minute, okay? Now. So at this point, we are doing the sounding part. Okay. It's a 80 megahertz antenna, and this orange rod you can see here is a bistatic, because that there is a separation between transmitter and receiver. Here transmitter receiver in the same position. You have to just drag it with your spacing. So just like you are walking, and you will be dragging at that speed. Okay. So this field data or this field photograph is from Chandraketu God, the Ganga side. Okay. So this is called the bistatic antenna, 80 megahertz. This is 200 megahertz, and these are the ground couple. Because you have to keep the antennas on the ground, uh, and so if you want to, and this can using this system, you can use this system, this right hand side system, or using this system, you can use up to 16 megahertz frequency. So we are doing 80 megahertz. 80 megahertz has less depth of penetration than the 16 megahertz. If you want to find a deeper penetration, then you have to go for 16 megahertz. And as water has a high dielectric constant than the other material, so water generally give you a good contrast, even if you are using a low resolution system. So 80 megahertz low resolution, this frequency, this has low depth of penetration. Left side figure, the antenna has a low depth of penetration than this 80 megahertz, but will give you the high resolution data, and this won't give you the high resolution data as comparing to the 200 megahertz. Again, 16 megahertz will go like give you very low resolution data, but it can see up to much depth, and this can be used for GPS system here. So for 80 megahertz, we have used two dot. These are the basically the antenna, just like a radio antenna. We used to do the folding antenna. You remember in on a radio, there is a several component of this antenna is there. Then that's called the telescopic thing. That one coming out of another, just like a folding ছাতায় যেরকম থাকে হ্যান্ডেলে. Okay, same thing was there also. There is a telescopic antenna is there. So I have used here 60 centimeter, which will give you the 80 megahertz. If I have used 60 centimeter component, this orange one, then the telescopic 120 centimeter, which can go or extend up to 120 centimeter. So this is the telescopic, just like a folding umbrella, or just like the antenna we used to have. Okay, so this will give you the idea of this will give you the 16 megahertz configuration. So it will be huge. That's why there are some adjustable antenna support is there. So see, 1.2 meter, 1.2 meter, and so it's around 1.8 meter, 2 meter. So 2 meter means 6 feet. So this side there will be 6 feet long. This side this will be 6 feet long. That antenna you can only use in the coastal area or in the fluvial geometry. Other than we didn't use really the 60 megahertz. Okay. Now this is the 26 or 2.6 gigahertz antenna. This type of antenna generally used for concrete inspection. Okay. So there will be this is a ready-made sheet you they provide you the manufacturer, and you will be putting the ready-made sheet on the floor or on the place you want to survey on or on the wall. So if you want to find out the void space, this type of antenna is very useful. It's a very high resolution antenna, and one thing you can notice here that it's a 200 megahertz antenna, and it's a 2.6 gigahertz antenna, 2600 megahertz antenna. If the frequency is increasing, the size of the antenna is decreasing. Got it? This is a 100 megahertz monostatic or bistatic antenna. Tell me, this one, the top one, people are dragging. Tell me, it's a monostatic or bistatic antenna.
So the left one.
No, that one, this
Okay.
one, the right
So
one,
that
100
is
megahertz.
the,
So it's a monostatic or bistatic.
yeah, bistatic.
So there is a separation between the transmitter and bistatic. So it's a bistatic. And see, this is how the 16 megahertz antenna, how big it is. Okay, so it's very difficult for to take the data. So in generally glacial deposit or glacial thing, it is working fine. One more thing, in our last class we have discussed that if the overburden is resistive, then GPR is good enough. We don't go for any wet or moisture land area or soil covered area. We generally go for resistive areas, so like dry sand is there or ice is there. Okay, simple ice is there. So what happened to ice? In ice, you could map up to 800 meter to 1 kilometer using these antennas. Whatever the antenna we're using, and we are getting up to 35 meter in the sediment, we get up to 800 meter in the glacier or this permafrost region. Why? Because the um, ice is very resistive comparing to the sediments. Okay. Due to the resistiveness, you can see up to 800 meters in this case. So this is a 100 megahertz. These are from GSSI basically. All these things, and GSSI first manufactured the GPR system. So this is the 100 megahertz antenna. Now, this is again from the GSSI. This table is showing you how far depth you can go. So 15 to 18 megahertz, 80 megahertz, you can see up to 50 meter. 50 meter, 150 feet. And it's generally used for geotechnical, aquifer mapping. 100 megahertz is there. 200 megahertz I have used many times. We have the system of this system 15 to 80 megahertz and 200 megahertz. Okay, these two systems we had. I mean, we have in IIT Kharagpur. And 400 megahertz is also used in sedimentological investigation, but it won't give you the much depth, but it will give you high resolution data. Sometimes in sedimentological study, there are some thinner bed or which needs to be identified. Like you are doing a heavy mineral survey, and that can be done heavy minerals in coastal things. So it's a placer deposit, and I don't know about much about the geology of the heavy minerals. I have very limited knowledge, but I know how it looks like in a GPR system. So in a coastal area like Chandipur, Gopalpur, in that portion, there are a lot of heavy mineral like zircon. I don't remember, I don't know about much about the heavy minerals, but it will appear that deposit will be clearly identified with the system with this 400 megahertz. It is a high resolution system. Now, let's talk about the transducer. Transducer or transmitter is there is a broadband electromagnetic wave or impulses, and you know the principles. Similar